Hello and welcome to the channel. If you are building self-hosted applications on Kubernetes, especially with lightweight distributions like K3s, you probably hit a wall when trying to make those services accessible from the outside world. Specifically, how do you reliably expose an Ingress controller in a highly available cluster? In this video, we'll tackle that challenge heads-on. I'm going to deploy a simple 3-node cluster running in highly available mode and walk you through 3 different methods for exposing your K3s Ingress to the internet, ensuring it stays up and running even if one of your nodes goes down. We'll cover using NodePort with a floating IP managed by KeepAlived, explore MetalLB as a software-defined load balancer within your cluster, and dive into the modern approach of CloudFlare tunnels with multiple replicas for robust and secure access. My name is Philip. Let's get started. Alright, let's dive into setting up our Kubernetes cluster. If you want to follow along step by step, the commands and configurations are available in my GitHub repo. Check the description for the link. So, in any standard Kubernetes setup, you have worker nodes that run your application and control plane nodes that manage the entire cluster. For a truly resilient, highly available Kubernetes cluster, you need redundancy. That means having multiple worker nodes and multiple control plane nodes. If one goes down, others can take over. Now, in a production environment, you typically have dedicated machines for the control plane and dedicated machines for the worker nodes. However, for this demo, we are going to keep things a bit simpler and use K3s, a lightweight Kubernetes distribution. We'll set up a 3-node K3s cluster where each node will act as both a control plane member and a worker node. K3s will handle its configuration and state using a clustered etcd data store, making our control plane itself highly available. Let's start with the first node. We'll run the K3s installation script using curl. Let's break down this command. Cluster init. This is crucial. It tells K3s that this is the very first node, initializing a brand new cluster and its etcd data store. K3s token. This sets a secret token. We'll need this exact token for other nodes to join the cluster securely. Cluster CIDR and service CIDR, these define the internal IP address ranges Kubernetes will use for pods and services. Disable service LB. K3s comes with a simple built-in service load balancer. We are disabling it because we'll install and manage our own load balancing solution later. Disable network policy. We are disabling the default network policy controller for simplicity in this setup. Disable Traefik. K3s also includes the Traefik Ingress controller by default. We are disabling it as well, as we'll set up our own Ingress later. Great. Node 1 is initializing. Now, let's move to the second node and have it join the cluster. Notice the key difference here. No cluster init. We are joining an existing cluster, not starting a new one. K3s URL, this tells the new node where to find the Kubernetes API server of the existing cluster running on node 1. K3s token. This must match the token used on node 1 to authorize joining. Server. Importantly, we are still using the server command. This means node 2 is joining as both a control plane member contributing to etcd and API server availability and a worker node. This gives us high availability for both aspects. Now, we'll repeat the exact same process for the third node, ensuring it also points to the first node's API server and uses the same token. Okay, all 3 nodes should now be part of the K3s cluster. To interact with our cluster using kubectl, let's go back to node 1 and copy the K3s configuration file to the standard location. This makes the cluster configuration accessible to your user account. Let's verify our setup. First, let's list the nodes. You should see all 3 nodes listed as ready, and you'll likely see control plane, etcd, and master in their roles, confirming they are all participating in the control plane. Next, let's check if workloads can be scheduled on them. We'll look for taints, which can prevent pods from running on a node. You should see taints none for each node. This confirms that pods can be scheduled on all 3 nodes, meaning they can act as workers too. So, to sum up, we've successfully created a highly available 3-node K3s cluster. Thanks to clustered etcd, each node is running both control plane components and can run our application workloads. We use the default Flannel CNI for networking, but we specifically disable the built-in service load balancer and Traefik ingress controller. Alright, we now have a 3-node K3s cluster up and running, but here's the big question. How do we actually get external traffic into our applications inside the cluster? That's where an ingress controller comes in. For this demo, we'll be setting up Traefik, and we'll install it using Helm, the Kubernetes package manager. First thing first, let's add the official Traefik Helm repository. Then let's update Helm to make sure it has the latest information about the available charts. Now, how do we expose traffic to the outside world so it can actually receive traffic? In a typical cloud environment, you'd use a load balancer service. However, we disabled the built-in K3s service load balancer earlier, and we are not running in the cloud environment anyway. So, for this demo, we'll use NodePort instead. Here's a quick overview of how NodePort works. Kubernetes picks a high number port, usually above 30,000. That port is open on every node's external IP address. When traffic hits that port on any node, Kubernetes forwards it to our Traefik service, and from there to the right pod. It's a straightforward and cloud-agnostic way to get traffic into the cluster without an external load balancer. Alright, let's install Traefik using this NodePort strategy. A quick breakdown of the important flags we'll use. Here we define we'll be installing Traefik in the kubesystem namespace, a common place for cluster-level add-ons. This tells Helm to expose Traefik as a NodePort service, not as a load balancer. Here we define that we want to use a daemon set instead of a regular deployment, ensuring there's one Traefik pod running on each node. That's critical for high availability and efficient load balancing of traffic. Let's now run the install command. Traefik should now be deploying. Let's check on a few things. First, let's look at the Traefik daemon set. There it is. If we dig deeper, we'll see it has pods on all 3 nodes. Next, let's check the service to find out which node ports we are assigned. We see HTTP traffic is mapped to port 32656 TCP, and for HTTPS traffic is mapped to port 31377 TCP. So now, when traffic hits port 32656 on any node, it gets forwarded internally to Traefik cluster IP, which then routes it to one of its pods. With Traefik ready, let's deploy a simple test application to see it all in action. I've prepared a manifest file called whoami YAML. Let's apply it. This includes a deployment for the whoami application with 3 replicas for high availability, a cluster IP service to give the pod a stable internal IP, not directly reachable from outside, and most importantly, an ingress resource that tells Traefik, if you receive traffic with the host header whoami Linux Cloud Hacks OVH, route it to the whoami service that listens on port 80. Now the moment of truth. Let's try accessing our application from outside the cluster. We'll curl each node's IP address on the NodePort, making sure to include the proper host header. We see a response from the whoami service. No matter which node you hit, Traefik picks up the request, matches the host header to the ingress rule, and forwards the traffic to one of the whoami pods. So to recap, we installed the Traefik ingress controller as a highly available daemon set, we exposed it using NodePort service, we deployed a sample application, and we configured an ingress resource to route external traffic based on a host name. And just like that, we can now reach our application from outside the cluster just by hitting the NodePort on any of our nodes. What now? We want to expose our application to the internet. Our router has a single public IP, but our K3s cluster consists of 3 nodes on the LAN, each with its own private IP. The first method I'd like to demonstrate is using an external floating IP. In this setup, we assign a new IP address to one of the nodes. If that node goes down, the IP is automatically reassigned to another node. Let's walk through the setup step by step. I will start by assigning a dedicated external IP address to our ingress. To do that, let's go to node 1 and open its network configuration. Next, let me add a second IP to the ETH0 interface. We'll later use that IP for our ingress. Let's now save and reload the configuration. What just happened? Our primary network interface now has two IP addresses. Let's assign the new IP to our ingress. To do that, I will go to Services and then edit the Traefik NodePort service definition. Let me add a new parameter called external IPs. Here we'll specify our secondary address. Do you see that? Our ingress has now an external IP assigned. To be precise, the IP address is external to the cluster, so clients from outside Kubernetes can connect. Let me demo that. I will go to a different PC within the network and try accessing our cluster via this new IP. Works. Two things to mention. The IP is external. External IP is not the same as public IP. Public IP is an IP reachable over the internet. External IP is an IP on the host network reachable from outside the Kubernetes cluster. In our case, it's a private IP. So in order to expose the service to the internet, we still need to perform a NAT on the router. The router is configured, so when the traffic arrives via WAN 1 on the TCP port 80, it will be forwarded to NodePort of our new IP 192.168.12.30. Let me try to access our application from the internet. Works. Important thing to mention. You can assign an external IP to a service only if it's a NodePort or a cluster IP. You cannot use this method to assign an external IP to a service of type load balancer. And yes, you've heard correctly. You could assign an external IP directly to a cluster IP. So technically, we could bypass ingress and assign the external IP directly to the cluster IP service in front of our application. Let's try that. I will edit our WhoAmI cluster IP service and add a new external IP. There you go. This technique is often used to expose a non-HTTP services. Getting back to the topic, everything looks perfect. We can access our application from the internet, but what if Node 1 goes down? Let's find out. I will shut down Node 1. Let me try to access our application now. We no longer can access the service, despite we have two nodes operational. Unfortunately, the external IP was assigned to Node 1, and Node 1 is down. To solve this issue, we'll use a technique called floating IP. Here's how it works. All nodes join a multicast group. One node is elected as the master and is assigned a floating IP address. The master node periodically sends advertisements to the multicast group to signal that it's active. The other nodes, known as backup nodes, listen for those advertisements to monitor the master status. If the backup nodes stop receiving advertisements, they assume the master node is down and initiate a new election to select a replacement master. It may sound complex, but it's very easy to set up. I've put node 1 back in operation. Let's first remove the second IP. To do that, I will open the network configuration file and remove this line. Then let's reload network configuration. Okay, the second IP is no longer there. To set up the floating IP, we'll use the KeepAlived, which implements VRRP, Virtual Router Redundancy Protocol. I have KeepAlived already installed. Let me go through its configuration. We set the node to master. Master is the node that actually owns virtual IP. Then we define the virtual router ID. It identifies the group the router belongs to. Basically, it associates multiple physical nodes with a single virtual router that shares a single virtual IP. Then we have priority. Node with the highest priority will be selected as master and claim the IP. Here we define how often to send advertisements. In our case, it's every 1 second. Finally, we have the virtual IP. KeepAlived supports other features like load balancing or connection state synchronization. We are just using a very basic configuration. Okay, let's start the KeepAlived service. If we look at the KeepAlived status, we'll see that instance entered the master state, hence we got the virtual IP assigned. Let me go to node 2 and show its KeepAlived configuration. It's identical to the master node, same virtual router ID and same virtual IP. The only difference is the initial backup state and lower priority. Let me start KeepAlived service on backup nodes. If we look at KeepAlived service status on node 2, we'll see it operates as a backup. Basically, the virtual IP is not assigned to the node, but it's ready to take over if master fails. Let's now test our setup. I will try calling our application from outside the cluster. Works. Now, let me shut down node 1. That's the master node. If we go to node 2 and check KeepAlived status, we'll see it took over the master role. As a master, it claimed the virtual IP. Let's repeat the connection test. Works. Our traffic got directed to node 2, that's the actual master. We've achieved our goal. We exposed Ingress controller in a highly available manner without using an external load balancer. All it took was assigning an external IP to an Ingress and setting up a floating IP with KeepAlived. Few considerations. For the VRRP to work, your network needs to support multicast. That's usually true for on-prem systems, but most cloud providers do not support multicast. Anyway, in a cloud environment, you can use a load balancer to expose your traffic. Second thing is, if you bring the node 1 up, it will be elected master again. You can change that behavior with preemption configuration. Third thing, the control plane needs to be highly available. So, even though one of the nodes failed, the cluster survived as it still has two healthy control plane nodes running. If we had only a single control plane node, then if it failed, the pods would continue to operate, but we would not be able to deploy new pods, automatically recreate pods if they fail, or make any changes in general. Hence, it's very important to have a highly available control plane. Next, the Ingress controller needs to run on multiple pods. If we would have only a single pod for our Ingress, then if it went down, all the traffic would go down, at least for some time. Lastly, in this approach, the traffic enters our cluster always via node 1, or to be precise, the node that is elected master. Exposing Ingress using NodePort with a floating IP does work, but it's a bit cumbersome. You have to manually allocate an IP address and set up VIP failover, which involves configuring the operating system outside of Kubernetes. Let me show you a more streamlined alternative, MetalLB. MetalLB lets you expose your workloads using Kubernetes built-in load balancer service. It simplifies things by automatically assigning an external IP from a predefined pool. This external IP can be advertised to the rest of your network in two main ways. Layer 2 mode. In this mode, MetalLB responds to ARP requests for the IP, letting devices on the same network reach your service directly. This is the simpler option and doesn't require any special networking hardware or any setup in the operating system. Second option to advertise the IP is BGP. In this mode, MetalLB peers with your router and advertises the IP through BGP, allowing for more advanced routing setups. I have detailed video that guides on both methods if you'd like to explore them further. For this demo, I will use the Layer 2 approach since it's easier to set up and works in most environments. To start fresh, I removed both our applications and the Traefik Ingress controller. Let's begin by installing MetalLB using the Helm package manager. First, I will add the MetalLB Helm repository. Next, I will update the repository to fetch the latest charts. Now, I will install MetalLB in the kube system namespace. Once installed, we need to configure MetalLB to use Layer 2 mode for IP advertisements. I will start by applying the Layer 2 configuration. Next, I will define the IP address pool MetalLB will use to assign external IPs to load balancer services. Here's the configuration. Make sure the IPs in the pool belong to the same subnet as your network interface and are excluded from DHCP. Let's apply the configuration. From this point forward, whenever we expose an application using a load balancer service, MetalLB will automatically assign an external IP and handle the network advertisements. Now let's deploy the Traefik Ingress controller, this time using a load balancer service instead of NodePort. We'll also configure it to run as a daemon set for high availability. With the Ingress controller in place, let's deploy our application. We can check the deployment with K3s. We'll see 3 pods, one on each node. Let's look at the Ingress configuration. It has an external IP assigned on TCP port 80. This IP comes from the first address in the MetalLB pool. If we check the list of services, we'll see Traefik service is of type load balancer, has an assigned external IP, and listens on port 80. Note, since we deployed Traefik as a daemon set, there's one pod running on each node. It's worth mentioning that MetalLB handles the load balancer IP entirely at the Kubernetes level. You won't see the IP on the host network interface. I've also updated the router to forward TCP port 80 to allow external access. Now, let's test the application. Success! Let's try a failover test. I will shut down node 1. After confirming node 1 is offline, let's try the connection again. It still works. Great! MetalLB in Layer 2 mode has several advantages. It's easy to deploy as no OS level changes are required. Everything is configured via Kubernetes manifests. It handles failover automatically. If a node fails, another node takes over the IP. Moreover, MetalLB handles IP allocation, so you don't need to set external IPs manually. However, there are also some limitations. Only one node holds the IP at a time. All external traffic goes through it, which could become a bottleneck. Also, there may be a slight delay during failover as ARP updates propagate. Lastly, Layer 2 mode doesn't work in most cloud environments due to how they handle ARP and IP routing. For instant failover, true traffic distribution, and higher scalability, consider using BGP mode. It does require a BGP-capable router and more complex setup, but provides real-time failover, load-balanced traffic routing, and better scalability. Check out my dedicated video where I demo the BGP setup in detail. The two methods I've shown you so far are solid, but they come with a few drawbacks. First, they don't support true load balancing across nodes. Traffic always enters through a single node and only then is distributed internally. This means the high availability model is effectively active-passive. Second, both approaches require a public IP address, which means exposing your interface directly to the internet. But what if I told you there's a simpler and more secure way to expose your Kubernetes workloads? One that does not require a public IP, yet still provides high availability and load balances traffic across all your nodes? Enter CloudFlare tunnels. Here's how it works. You deploy a daemon set that runs one CloudFlare pod on each node. Each of these pods creates a secure tunnel from the node to the CloudFlare network. CloudFlare handles incoming client connections, terminates TLS, and distributes requests across all active tunnels. If any tunnel goes down, traffic is automatically routed through the other tunnels, ensuring resilience and uninterrupted access. Let me show you how to set it up and see it in action. Before we begin, there are a couple of prerequisites. Your domain must be managed by Cloudflare DNS, and also you need to register for Cloudflare Zero Trust. I have separate videos covering both of these steps if you are interested. Here's what we have. A 3-node K3s cluster with a highly available control plane. Each node is running a traffic ingress controller. In front of the traffic pods, there's a load balancer service, but it does not yet have an external IP. It only has an internal cluster IP. The cluster IP service points to our application on the backend. We'll begin our setup by installing Cloudflare D on one node. To perform tunnel configuration. First, I will add the Cloudflare's GPG key. Then I will add the Cloudflare D repository. Refresh packages list and install Cloudflare D. Finally, I will disable the Cloudflare D system service. We'll run it only from Kubernetes. Once we have Cloudflare D installed, let's authorize our local machine to manage Cloudflare tunnels. To do that, I will issue Cloudflare D tunnels login command. Let's now open the link in the browser, select our domain, and click Authorize. We now have a certificate saved locally. Now let's create a new tunnel with Cloudflare D tunnel create command. This creates a tunnel and generates tunnel credentials saved in JSON file. We need to keep this file secure. Anyone with access to this file can connect to our tunnel. We can verify the tunnel in Cloudflare dashboard under Zero Trust, Networks, Tunnels. Tunnel is there, but it's not yet active. Let's proceed to the Kubernetes setup. First, I will read the tunnel credentials into a Kubernetes secret. I already have a daemon set manifest ready. It deploys one Cloudflare pod per node. Each pod will establish its own connection to the Cloudflare network using credentials from the secret. From Cloudflare's perspective, these are multiple connectors for a single tunnel. Cloudflare will then create a reverse proxy that routes traffic from any subdomain of Linux Cloud Hacks OVH to our traffic ingress controller. Mind that we are accessing our traffic ingress via cluster IP. Okay, let's apply this manifest. we see both daemon sets, CloudFlare D and Traefik ready. In the CloudFlare dashboard, we have single tunnel with 3 active connections, 1 from each pod. Mind that all 3 connections originate from the same ISP, but if we have more than one internet link, we could connect via various ISP, further improving service availability. Finally, let's create a wildcard CNAME record in CloudFlare DNS to route all subdomains to the tunnel. OK, CNAME has been created. Let's verify the record in the CloudFlare DNS dashboard. It's there. Now let's test the setup using curl. I will use HTTPS as Cloudflare offloads TLS. Works. Moreover, the traffic is balanced across multiple nodes. To simulate a failover, I will shut down node 1. Let's check the connectors again. Only 2 remain active. Yet, the application is still accessible. The cluster continues to serve traffic thanks to remaining 2 tunnel connections. So there you have it. We have successfully set up a highly available K3s cluster and explored 3 robust ways to expose Ingress controller to the internet. Using NodePort with a floating IP managed by KeepAlived, leveraging MetalLB as a software load balancer, and the modern, secure approach with CloudFlare tunnels and multiple replicas. If you found this video helpful in getting your self-hosted Kubernetes application accessible, please give it a thumbs up. Don't forget to subscribe for more Kubernetes and cloud-native content. All the commands, manifests, and the link to the GitHub repository are in the description below, along with links to other videos I mentioned. Which method are you planning to use, or do you have another favorite way to expose your K3s cluster? Let me know down in the comments below. Thanks for watching.